Hi, this is Tom Craven from Ramic Connected Systems. Today we're going to talk about our predictive maintenance offering with some focus on our artificial intelligence simulation models. Most companies recognize the potential benefits of predictive maintenance. The slide here shows reduced maintenance costs, significant reduction in breakdowns, less downtime, increased productivity, and a pretty compelling return on investment, 10 to 1 in this case. This is based on industry averages, so of course individual applications could be higher, could be lower, but 10 to 1 ROI is worth stopping to consider. However, if I come into your plant and say, hey, I want you to spend $100,000 and 2-3 years down the road, that's going to pay off $1 million, you're going to say, well, gee, I don't really have $100,000 to spend right now, and I'm not entirely sure I believe you. Well, I don't blame you. So let's look at how we can get a faster return on investment, generate some short-term ROI, limit the upfront costs, and still stay on track for the longer-term ROI associated with predictive maintenance. For starters, we can significantly reduce the upfront cost by leveraging software as a service. The idea here is that there's no servers to buy, no software to install and configure, and it can be fully set up by industry experts. The most cost-effective way to do this is cloud hosting. However, on-premise is an option as well. In that scenario, we would deliver a pre-configured server or server image. It's going to cost a little bit more upfront, but there's still significant cost savings compared to a traditional in-house developed system. One of the ways that we can help assure short-term return on investment is to start with condition monitoring. Condition monitoring is a very good way for most systems to generate some short-term return on investment. This is simply monitoring vibration, motor current, maybe temperatures as a leading indicator to a pending failure. This is easy to set up and there's immediate value. The downside is there's no actual predictions generated out of this. It's just saying, hey, this system's deteriorating and it needs some attention. The other limitation with condition monitoring is it doesn't work as well for more complex systems. So if you have a lot of changing ambient conditions, changes in raw material, running multiple products on the same line, maybe multiple vibration axes, you can get a lot of variables thrown at you at once, and you can't simply set a single threshold and say, well, this is my leading indicator. In those situations, you're definitely going to need some sort of artificial intelligence. Many predictive maintenance solutions are based on pattern recognition. The idea here is we'll run mathematical algorithms on time series data which can flag anomalies, and then those anomalies are related to a failure event. The challenge with this is you got to collect a lot of data, usually over a long period of time, and you also have to suffer through multiple failures in order for this system to learn the cause and effect relationships. The problem, of course, is most customers are not willing to suffer through many failures in their system after they've paid for an expensive predictive maintenance system. And in reality, the cause and effect relationships in many industrial applications are already known. So for example, let's look at an industrial application where we already know many of the cause and effect relationships. We know that vibration is often a leading indicator of failures. There's multiple places where we can look at the vibration, but that's often an early warning signal. There are also critical warnings. Obviously, if your motor bearing temperature is shooting up, something bad's about to happen. We can also look at the process variables, things like the pressure and flow of a pump. As those values are changing, we can say, yeah, this pump is needing to work harder than it used to. These are things that are indicating there will be a failure. Now, we already understand at a high level the cause and effect relationships, and people have studied this in depth and actually have models built that we can plug in and use to predict when a pump is going to fail. Now, in your individual system, the timing of those failures has to be learned gradually. We can start with estimates based on other applications, but the system uses artificial intelligence to fine-tune these relationships. This is vastly different than trying to learn all the relationships from scratch. You start to get return on investment right out of the gate with this type of simulation. So we can take all this cause and effect relationship running inside of the simulation model, and we end up with results that are going to tell us the current remaining life of that device, in this case a pump. We start out at a nominal warning phase where we say, hey, there's some leading indicators. We're starting to deteriorate. The life is getting shorter. Those conditions are then elevated as we start to see increased values or maybe some changes in the more critical variables. We can do all this without actually getting to the actual failure. And so these models can tune themselves over time without waiting for a catastrophic failure to occur. But we can predict the date more and more accurately the longer the system runs. So you have an artificial intelligence layer helping the system get smarter and smarter, but you have predictions and you have value from day one of running the algorithm. Now, there are still instances where pattern recognition is the preferred method, but for the vast majority of applications, we can plug these cause and effect algorithms in, fine-tune them over time, and get a much faster return on investment for your predictive maintenance systems. For more information on predictive maintenance, please visit our website at www.rramac.com or call or email us with the information on the screen. Thank you very much for your time. Have a great day.